These are your 0-2 notes on number sets. This is the only section from Chapter 0 that we will be learning about. It's just a prerequisite into Chapter 1. And so it's a really important section because it talks about a lot of the vocab that we use throughout the year in algebra and beyond in regards to number sets. So if I talk about a rational number, it would be nice to know what the heck rational even means. Or if I talk about an integer, what that actually means. So we're going to take some time. I'm going to define them. I'm just going to describe them, and then I'll draw a picture if I can on a number line. Rational and irrational numbers are difficult to represent on a number line because you can't necessarily tell the difference of which one I'm plotting. Is it a rational or an irrational? So I'll just give you a description of those. So for natural numbers, it is just that. These are the numbers that naturally occur to us. So if you think back when you first learned how to count, or you watch a toddler count, they start counting at 1, and then they go in whole number increments, 2, 3, on and on and on. So they start at 1, and the numbers increase in whole number increments, no fractions, no decimals, no negatives. On a number line, what that will look like is just a dot at all of those whole numbers. And so we'd have a closed dot at 1, signifying that 1 belongs in this set, 2, 3, and then to say forever in the positive infinity direction, you just block in that right arrow and that says forever, never, never. Okay, we're not shading in between. That would include all the decimals and fractions in between those numbers. So it's just 1, 2, 3 to positive infinity. Whole numbers just add on 0 to the natural number set. So the dot, dot, dot implies forever, never, never in that same pattern. Okay, so whole numbers adds on 0. So what we can say is the natural numbers, all of these numbers, are a subset of the whole numbers. They belong within the whole numbers. The only difference is 0. And so to look at the whole number set on the number line, we'd include 0, 1, 2, 3, on and on and on. So we just add a closed circle at 0, 1, 2, 3, and then we're going to block in that right triangle again, symbolizing positive infinity. We're going to continue this forever, never, never. Okay, so you're going to notice throughout algebra and the rest of your math that they want us to show it mathematically, algebraically, but they also want us to represent the numbers graphically. So a number line is a good way to show the graphical representation of these numbers. Integers. Integers takes all of the natural numbers, all of the whole numbers, and then does the opposite of them as well. So this is where our negative whole numbers come into play. So integers, I'm going to do the dot, dot, dot first, implying we go all the way to negative infinity. Negative 2, negative 1, 0, 1, 2, dot, dot, dot. And so that's implying that we're going forever, never in each direction. Notice, still no decimals, no fractions. It's just the positive and the negative whole numbers and 0. So really, the whole numbers are subsets of integers, and natural numbers are a subset of integers. The entire set of natural numbers belongs in integers, and the entire set of whole numbers belongs in integers. So when I graph this on a number line, I'm going to have a point at negative 2, negative 1, 0, 1, 2, and then I also want to block in the negative infinity arrow and the positive infinity arrow, implying this goes on forever and ever. Irrational numbers and rational numbers are really close related, so I can't really give you the picture of them on the number line, but I'm going to give you a description of both of these. So this is where our fractions and decimals enter in. They can be positive and negative, so don't worry about the signs of these things. If you see ugly numbers, okay, so rational numbers are the nice ugly numbers, I should say, and then irrational numbers are the ones that are really ugly. So rational numbers are your terminating oops, I think I spelled that wrong. And repeating decimals. So if the decimal terminates, means it ends, or if it doesn't end, if it has a pattern. So these are your decimals that can be written as fractions. I can give you a couple examples of these. So a terminating decimal would be 0.25. It ends, doesn't go on forever, never, never. And then a repeating decimal would be like something like 0.3, where you put the bar over it, as long as you see the pattern. Both of those can be represented as fractions, a quarter and a third. So it's your terminating decimals that end and your repeating decimals. So then irrational numbers, just is a prefix for not. So we're talking about the not rational numbers. So if it's not rational, it's irrational. So that means your non-repeating and non-terminating decimals. So a couple of examples of irrational numbers. Non-repeating, well, what's the most famous non-repeating decimal would be pi. So anything involving pi is going to be irrational. Another irrational that we're really not used to at this point would be a non-perfect radical. If I type in the square root of 5 on my calculator, it's going to give me a really ugly decimal. It's going to go all the way to the end of my calculator and beyond. It never ends and it never repeats. So I can't really put those on the number line because I wouldn't be able to distinguish between which ones are the rational or the irrational. Real numbers encompass all of the above. So all of those other numbers, rational and irrational numbers, whole numbers, integers, natural numbers, are all subsets of real numbers. So I'm going to give you a picture of this on the next slide, and I think it'll help you out. On the number line, though, it is every single number that belongs on the number line. So I really have this black number line, but because it includes every number on the number line, I could plug in -2, -1, 1, 0, 1, 2, 3, 1.5, pi, negative pi. All of them are on here. And so what would happen is I would plot, and all these numbers would get so close together, and as soon as I put that number on, I could find one right next to it. 0.1, 0.2, 0.3, 0.4, 0.44, 0.49, 0.49999. Eventually, you would see every single number, no gaps whatsoever. And so the entire number line would be covered. So another picture of this, another way to look at this, is in a geometric figure. And so we like to use circles or squares to help us understand these number sets. So a lot of times in math, it's just like a Venn diagram. You guys are used to Venn diagrams that overlap, I think, from different classes. Okay, so that's two sets of data or numbers or characters in a poem or a story. And then the overlap is the things that they have alike, and then their differences are on the outside. So this is the same concept. It's just, if you notice, these are subsets. So one whole set of numbers is inside the other set. The overlap is every number. So if we want to work through this, the entire set, the entire rectangle is real numbers. And then real numbers, and the real numbers are split up into two different categories. You are either a rational real number, or you are an irrational real number. Now, I want you to understand that both of these go on forever, never, never. There's an infinite amount in each. So I know it looks like there's more rational numbers than not. That's incorrect. So I don't want you to have you misunderstand the connection here of these number sets. The only reason I made rationals bigger is because there's more subsets within the rational numbers. So I kind of want to give room to show you those subsets. There really are no irrational subsets. It's just irrational numbers. So we can get those out of the way. Let's talk about those first. Non-repeating, non-terminating, decimals. And so that's pi and non-perfect radicals. So for the most part. Those are the two famous types. So if you see something that's not perfect that's a radical, like the square root of 5, then you know it's irrational. If you see anything involving pi, you know it's irrational. Whoops. So there's your irrationals. Your rationals then are broken into subsets. So let's go with the littlest one first. Here are your natural numbers. Within your natural numbers, you have 1, 2, 3, ... Your whole numbers are the next set out. The whole numbers include all of those natural numbers, so I don't really have to write them down again because they're already in that natural set. So do you see how that pink circle is fully encompassed in the yellow? So I have all of those. The only thing I'm going to put out in the yellow is 0 because that's the only thing we add for whole numbers. I don't want you to think that 0 is the only number in the whole number set. It's 0 plus all of those natural numbers. And then the blue, the dark blue, is a set of integers. So the integers has all of those whole numbers, 0, all of the natural numbers, 1, 2, 3. So the only thing that would be on the outer edge here would be my negatives. -3, -2, -1, on and on and on. And then the rational number encompasses all of those. So it has all the naturals, the wholes, the integers, and then the terminating and repeating decimals. So in this, I can put 3/4. I can put -0.5. I can put -1/3. Okay, and then maybe a repeating 0.1 repeating. So those are all the rational numbers, positive and negative. But in addition to those numbers, an integer is a rational number, a whole number is a rational number, and a natural number is a rational number. So let's just go through and name the sets that each of these belong to. So you can kind of use your graphical organizers there. So the first thing is I like to find the smallest set that it belongs to and then work your way out. These are all going to be real, and they're all either going to be rational real or irrational real. And they could have more than that, but you have to have at least 2 sets for every number. So when you look at -2/3, it is not a natural number, it's not a whole number, and it's not an integer because it's a fraction. If I actually put that in my calculator, -2/3 ends up being -0.6 repeating. Okay, now on your calculator, it's going to throw a 7 at the end because your calculator rounds off at the very end. So it's still repeating. And so since it's a repeating decimal, it's going to be a rational, real number. So those are the 2 sets that it belongs to. 9.9999 ... is telling me that it is also repeating. I could have just put 9.9 repeating. So this too is a rational, real number. The square root of 6, when I type the square root of 6 into my calculator, I get a really ugly decimal. It goes all the way to the edge of my screen. It doesn't stop there, it goes beyond. And so this is what an example of an irrational because it doesn't terminate. So it's irrational, but it's also real. And then the square root of 100, you want to simplify it. So if you type the square root of 100 in your calculator, you end up getting 10. So we really don't want to look at the square root of 100. We want to look at 10. 10 is a positive whole number, so that means it's a natural number. Which, if it's a natural number, it's automatically a whole number because that whole set of naturals are within the wholes, which means it's automatically an integer. And it's a rational, even though it's not a decimal, it's still part of that set. The only difference of rational numbers is they bring in those fractions and decimals, and then it's real. So if it's natural, it's all of those. The only thing it is not is irrational. You can't be a rational, irrational number. They contradict each other. The IR in front of irrational is saying not rational. So the least you can have is 2. You got to be real rational or real irrational, and then you could all have all of those different combinations. Okay, so at the end of our notes, we always have a lesson summary. This tells me that you were paying attention, you were listening, and you were following along in the notes. So I need you to name the sets of numbers that negative 27 belongs to. And in the practice problem, this is your first attempt, another attempt at your notes. So it just helps me, these two things help me know that you understand the concepts learned in a quick glance. So tomorrow when I check your notes, I'll be looking at this information. And you don't get graded on right or wrong, you get graded on effort. So good luck.